Well, good morning, everyone, and welcome. My name is Tim Horner. I'm with the Transportation Learning Network, and you're joining us today for the webinar Fiber Reinforced Concrete for Structural Components, which was a Mountain Plains Consortium Research 17-342. I'll introduce our presenter, Dr. Gadban, shortly. Today's presentation is hosted by the Transportation Learning Network. And as most of you know, that's a program managed by Upper Great Plains Transportation Institute at North Dakota State University. That's a partnership, a pooled partnership of the state DOTs of Montana, North Dakota, South Dakota, and Wyoming. We also partner with North Dakota LTAP and the Mountain Plains Consortium of Universities. And since this is a Mountain Plains Consortium presentation, I'm going to mention the universities that we get research from. Colorado State University, North Dakota State University, South Dakota State University, University of Utah, University of Wyoming, Utah State University, University of Colorado, Denver, and the University of Denver. So quite a list of universities that are partnering on research under the Mountain Plains Consortium grant, which also helps finance the Transportation Learning Network. Now our topic and speaker, our topic again is fiber reinforced concrete for structural components. And this presentation will cover research conducted by South Dakota State University on the Mountain Plains Consortium pooled partnership with additional funding from South Dakota DOT. And thank you to South Dakota DOT for helping with this research. Many of you know that there's little guidance for designers pertaining to the use of and testing of fiber reinforced concrete. There's also a lack of information about new fiber products that have been introduced in the market recently. So this presentation will go over results of a literature review and also some DOT interviews, summary of 21 mixed designs, and also suggested guidance for fiber reinforced design, construction, presentation, and testing. And our presenter today is Dr. Ahmad Gadban. He is a postdoctorate research associate at the Department of Civil Engineering at South Dakota State University. He received his PhD in civil engineering from Kansas State University and his master's and bachelor's in civil engineering from the American University of Sharjah in the United Arab Emirates. With that, I'm going to turn it over to Dr. Gadban. Look forward to the presentation.
Thank you very much, Tim, and good morning, everyone. And thanks for Transportation Learning Network for hosting me today. And thanks for everyone who's attending today. So my name is Ahmad Gadban, and today I'm going to be presenting the findings of our research, fiber reinforced concrete for structural components. So I'm going to be covering today the problem description, which basically tells us the incentive behind doing this research, then go through the objectives, the main objectives, and then the findings from the literature review and the DOT interviews, and then discuss our experimental setup and results, and finally conclusions and recommendations. So let's start with the problem description. As we all know, concrete deteriorates with time, which results in poor performance and ultimately in reduced life expectancy. And we always aim to increase the life expectancy of concrete, and that's why we introduced fibers into the concrete, creating fiber reinforced concrete, otherwise known as FRC, to help us into mitigating some of the problems that are inherent within conventional concrete. So the main reason behind the concrete deterioration is the fact that it has low tensile strength, which basically cause crack formation and propagation with time. This in turn results in a moisture and chloride penetration, which results in steel corrosion, basically reducing the capacity of the steel and therefore the capacity of the entire structure as well. And so here where fiber reinforced concrete come to save the corrosion of steel, if we say so. It enhances the tensile strength of the concrete and results in a better crack resistance. So we have these fibers which help bridging the cracks and preventing them from enlarging and propagating, hence protecting the steel from any moisture and chloride. So we have more crack density, but all of these cracks would be very small in size they wouldn't allow easily the moisture and chloride to penetrate into the steel corrosion, and that's how we enhance the overall crack resistance of for the concrete. Now, the reason we're doing this research is because of the fact that South Dakota DOT really have limited implementation of FRC. I believe they have few projects or few structures that have this FRC, and the last research that they have done is probably around 20 years ago or so. So there is pretty much lack of information for up-to-date information about FRC and what fibers are being used in the market nowadays. So there is a need for research to study basically the effect of these different fiber types and different fiber dosages on the properties of several properties of the concrete or FRC. So the main objectives is to identify best practices for design and construction of FRC. So this is by looking at previous studies within the literature, and also by conducting interviews with some personnel from DOTs around the US. And then the second objective is to assess the potential application, performance, costs, benefits, and drawbacks of FRC, and finally develop guidance for design, material selection, construction, testing, and application of FRC in South Dakota. And all of these objectives really are fulfilled through three main tasks. As I said, a comprehensive literature review looking at different previous studies that were conducted, and also some DOT interviews with some personnel that had some experience with previous projects that involved the use of FRC. And finally, the last task, which is the main thing that I'm going to be talking about today, which is the methodology, basically our experimental setup and results and what we get from those. So the main focus is going to be on our experimental setup and results, but I'll be going briefly into the findings from the literature review and DOT interviews, and for further more detailed study or what we found from the literature review, we have the report that was submitted to MPC, which I believe should be attached to this webinar, so it can be accessed for further information about these findings. But here I'm going to go through the main ones. So first of all, we constructed a fiber catalog, basically contains all the most commonly used fibers in the US nowadays, and all of their properties and whatever the manufacturer claims about their behavior and how they enhance the behavior of concrete. So we basically collected a comprehensive catalog of all the fibers, and we appended this to the report which I just mentioned. Now, going to the findings that we found from looking at the previous studies and DOT interviews, fibers can significantly decrease the consistency of concrete. So this is something that we should always keep in mind, as the workability of concrete really drops very low. And this is something that we also noticed in our experiments. So we should always keep in mind whenever we design fiber reinforced concrete, we expect the slump to drop as we add fibers, and so we should account for this by adjusting the whether it is the water to cement ratio or the water reducer and super plasticizers. Now, another finding is the fact that higher paste content can increase slump and reduce crack width for FRC. So, of course, there's also some disadvantages of using higher paste content. So this is something that also should be taken into account. So it's a way to increase slump and reduce crack width, but we should always keep in mind the other problems that are associated with higher paste content. Now, fiber balling can be reduced by choosing fibers with low aspect ratios and increasing paste volume and mixing time. So this is something that we actually did in our laboratory tests here. We increased the mixing time in order to make sure we eliminate any fiber balling and make sure that fibers will really act as they should be in the final product. Now, also increasing the paste volume, as I said, would also reduce the fiber balling, and specifically choosing fibers with low aspect ratios can also help in making sure that we eliminate this problem. The effect of fibers on the compressive strength of FRC is inconsistent. So this is one of the interesting things that we found in the literature review. We found several studies, each were showing different conclusions, basically completely contradictory conclusions. So one of them showed that the compressive strength is increased with by using fibers. Other studies showed it decreases. Other studies showed it does not affect the compressive strength. So basically, every possible conclusion was shown in the previous studies. And we'll see in our experiments, we actually aligned with one of these conclusions. But yeah, it's very interesting to see, even though normally we wouldn't expect fibers to have any effect on the compressive strength, since it's really meant to just to increase the tension capacity, the flexural capacity. Now, improved impact on freestyle resistance was also noted in some of the studies in the literature review. No significant effect on permeability. There is one study that was looking into see if there's any effect on permeability once we use fibers, but that study showed no effect. Better abrasion resistance when we use microfibers. Moving to the next slide. Steel fibers could produce hazardous surfaces, so this is something that we should keep in mind whenever we're using FRC with steel fibers in applications where pedestrians would be for pedestrians, basically, not for traffic, because this might cause injury, as the surface of the concrete would have some steel fibers protruding out from the concrete. So, but for traffic applications, it's really not a problem, as the traffic would soften these fibers with time once they drive on the surface of the concrete, which had these steel fibers. Field testing is mainly conducted through surface inspection and bond strength tests. So this is the only two methods that we found from the DOT interviews where the way they actually inspect the performance of FRC in the field. So by either surface inspection or by using the bond strength test. FRC experiences smaller cracks, as I said, with increased density. So we have more cracks with FRC, but they are smaller in size, which basically serves our purpose of making sure we increase the durability of concrete. Effect of fiber type and dosage is not sufficiently studied. We rarely found any studies where they actually look at the effect of different fiber types and different fiber dosages on certain properties of the FRC, which is something that we are focusing on in our experimental procedures that we followed for this research. Cost is doubled or sometimes even tripled, so this is something should be kept into mind whenever we choose FRC over conventional concrete. South Dakota DOT has no current specifications. We were able to find some brief specifications from other DOTs across the US, but as I said, they are just brief specifications, not very detailed. As for some of the differences between FRC and conventional concrete, there is really not much when it comes to design, preparation, mixing, testing, and finishing. FRC is pretty similar to conventional concrete, with the exceptions for few comments that we have here that we obtained from our study, which should be kept into mind whenever we design for FRC. And they are detailed within the guideline, which should be available in the MPC report, which is attached to this webinar, can be accessed. Now, so as I said, this is just a brief bullet points of what we found from the literature and DOT interviews. For further details, one could go to the MPC report. Now, moving into our experimental setup, here we show the different fiber types that we used. And as you can see, a majority of them are synthetic. So these four fiber types are all synthetic, which is basically the main focus of our research, because South Dakota DOT we're more interested in synthetic fibers as steel fibers would be susceptible to corrosion, especially in places where we have very harsh winters, just like we have here in South Dakota. So we really focus on synthetic fibers, but we also tried one steel fiber just as an extra, just to kind of compare it to the performance of the other synthetic fibers. And this table shows basically all the properties for each of these fibers that we used. One thing to note is the fact that the tensile strength of steel here, of steel fibers, are much higher than tensile strength of the other synthetic fibers, which most of them are around 90 KSI. Now for the mix design, we chose a standard mix that's used by South Dakota DOT. The water cement ratio was 0.38, and we had 21 mixes. All of them had the exact same proportions when it comes to basically the cement, the fly ash, coarse aggregate, sand, water, and the admixtures, basically chemical admixtures. The only difference between the 21 mixes is the fiber type and the dosage that was used. So we have one mix which is a control mix, which didn't have any fibers in it, and then 20 mixes which consist of 5 different types of fibers, each with 4 different dosages, around 0.2% by volume, 0.34%, 0.55%, and 0.69% for each of the fiber types. Now here, one thing to note for mixing. So as we said, for the most part, mixing FRC is pretty similar to conventional concrete. So we used ASTM procedures here. But the only difference is the fact that we had an additional 5 minutes of mixing after we added the fibers to make sure we have a uniform distribution of fibers and to make sure we eliminate any kind of fiber balling that might happen. So that's the only difference that we had in mixing compared to conventional concrete. For consolidations, all specimens were subjected to internal vibrations, as I said, because of the fact that slump was very low. When we added fibers compared to the control mix where we didn't have any fibers, we can notice a very notable decrease in the workability and the consistency of the concrete. So we had to use internal vibrations to make sure the concrete is very well consolidated within all the molds, and of course also to make sure the fibers would also be distributed uniformly. Now here are the properties or the tests that we conducted on the concrete that we chose to conduct and basically see the effect of different fiber types and dosages on these properties. So for the fresh tests, we did the typical ones, which are the density, slump, air content, and temperature, according to ASTM procedures. And then for the hardened concrete, we did the compressive strength, which at the beginning we anticipated that the fibers shouldn't have an effect on the compressive strength, but as we will see in the results, we did have some effect. And the main tests that we had are the flexural tests, as basically that's the main purpose of using fibers within the concrete, is to increase the tensile strength, which in turn increases the flexural strength. So we have these two different flexural tests. The third test here, flexural performance of fiber reinforced concrete, this one is the exact test that we conduct on conventional concrete. Basically the third point loading that we conduct on the conventional concrete. The second test, which is the average residual strength, this one is specifically made for FRC. So it does not really work in conventional concrete, since it basically requires the specimen to be pre-cracked before we actually apply any load to it. And so for conventional concrete, once we have basically conventional plain concrete, once we have it cracked, it does not really hold any load. So this average residual strength test is really not applicable for conventional concrete. So it's only used for FRC, and it measures the capacity of FRC and how much the fibers are increasing the flexural strength. So these are the main tests, but we also added another test which was not part of the initial proposal, which is looking at the impact resistance using the drop weight impacts test, which is adopted by ACI Committee 544, which is really qualitative in nature, but we chose to just do it just to have an idea about what would be the effect on the impact resistance. And finally, we verified the fiber distribution by saw cutting a cylindrical sample and looking into the interior cross section just by basically eye inspection and see the distribution of fibers and whether we have any fiber balling, just to make sure our mixing procedures and consolidation procedures really went well. So this picture shows the compressive strength, which is typical whether it is conventional concrete or FRC. We attach an extensometer here, which is used to measure the modulus of elasticity. And of course, we also obtain the compressive strength here. This picture here shows the flexural test, which is here ASTM C1609. And we had two LVDTs in the midspan on both sides, so one on this side and one on the other side of the beam. And this support is used to support these LVDTs, which measure the deflection of the concrete. Now, the average residual strength test, which is this one, ASTM C1399, it's also a test on beams, but the beams are different. The size of the beams are different. They are smaller in size compared to this test, but it's pretty much the same exact test. The only difference is that we have two loading periods. So this figure shows the loading schemes for the average residual strength test. So initially we place a steel plate under the beam, and then we load it till we have the first crack, which usually develops in the mid-span area. So once we have the first crack, and we will see a sudden drop in the load, and this is usually happen like below, when we have deflection below 0.008 inches. So once we crack the beam, we unload it, and then we remove the steel plate, and then now we have a cracked beam, and then we load it again, and this curve shows the second loading scheme, and then we record the load at certain deflections, at 4 different deflections here, and then these readings can be used to obtain our parameter, which is the average residual strength. Now, this picture here shows the impact test, the drop, which is this one, drop weight impact test, which is ACI Committee 544. So what we do is, from cylinders that we cast, we cut, I think, 2.5 inch thick samples, and then we place them here, and then we have a steel ball, and then we drop a hammer, and then we record the number of drops that result in the first crack, and then we record the number of drops that result in failure, basically. And so that would be the parameter that we use to kind of qualitatively get an idea about the impact resistance. And this picture shows the saw-cut side of the cylinder. And as I said, by visual inspection, we looked into all of them, and pretty much all of them seem to have a very uniform, random distribution. And we didn't see any notable fiber balling in all of our mixes. So we conducted statistical tests here. I'm not going to go into details into the exact mechanism of this test, but it's called the F test, and it basically measures the significance of the effect of fiber type on dosage on each of the measured properties. So this statistical test would give us an idea about whether the fiber types really, or the fiber dosage, different fiber doses really affected a certain property or not. And then after that, we can eliminate all of the properties that don't seem to have any changes based on the fiber dosage and type, and then we focus on the other properties, and we basically show figures, and as we will see in the consecutive slides. So we look at the p-value here. If it's less than 0.05, this indicates a statistical significance. If it's bigger than 0.05, then it's not statistically significant, and so we would conclude that that particular property is not really affected by the fiber type or dosage. So moving into our results here, first of all, this is just the table showing the statistical analysis. So just to give you an idea how we do it, just an example. As an example, here, if you look at, say, fresh air content, so we want to know the effect of fiber type, whether it's significant on the fresh air content or not. So we go to the p-value. It's way more than 0.05. Then we know that there's really no effect whatsoever. So the fiber type does not really affect the fresh air content. And then we go, for example, to the fiber dosage. We want to know the effect of fiber dosage in the fresh air content. We see it's 0.6271, way more than the 0.05 threshold. So there is really no effect, which is expected for fresh air content. And then we do the same with all other properties. And then based on that, we can isolate some of them. But we should note that due to the fact that our sample size is not really that big, so there could be some cases where we have a p-value that's more than 0.05, but then we look at the results and we see that there is some kind of slight effect. But for the most part, whenever we have a p-value less than 0.005, then we know that the effect is significant most of the time. Now moving to the compressive strength, we don't really see any effect. So here, this figure shows the compressive strength versus the fiber type, and this shows the modulus of elasticity versus the fiber type. Now the compressive strength is here is basically presented as ratio to the control compressive strength. So one would be exactly equal to the compressive strength of the control mix. Now, while we don't see any, of course, these different points are for different dosages. So we don't see any change when we change the fiber type. Maybe a slight change, but not really very significant. Also with the modulus of elasticity. But the thing that we notice here is the fact that all of them had a compressive strength much less than the control specimen. Also the modulus of elasticity, all of them had much less than the control modulus of elasticity. So we had some kind of maybe 15% drop in the compressive strength, and an average of 15%. So we noticed a drop in the compressive strength, which really aligns with one of the studies, or some of the studies that we found in the literature, but contradicts other studies which said it does not affect it, or they said it increased the strength, compressive strength. Again, we can't really, we couldn't really find the reason behind this. I believe we need really further studies that are focused on compressive strength to be able to identify the reason behind this drop. But in our procedures and based on what we adopted and what we followed, we didn't really, we couldn't identify the reason behind this drop. But it's something that should be noted, and whenever you design basically FRC, you should note that you might lose some compressive strength So this is something that should be noted until further studies are made on this specific property. Now, this figure here is just a comparison between the experimental modulus of elasticity and the theoretical modulus of elasticity. And this is just to kind of confirm to us that our experimental procedures really we had good experimental results. So, and we see that it's around the line of equality. So we have theoretical modulus of elasticity almost equal to experimental, and this gives us a confidence in our experimental results. Here I'm just showing a picture of one of the failed specimens, and they are pretty much the same, the failure mode as you see. So this is a compressive test for one of the specimens that had FRC, had fibers in it. And something that we notice compared to conventional concrete is the fact that you see the concrete is almost intact. So we don't see any crumbling of some parts of the cylinder as we would normally see in conventional concrete. And this basically tells us that fibers are really doing their job in terms of holding concrete pieces together. So bridging, as I said, their main mechanism is to bridge the cracks between whenever a crack happens in the concrete. And this shows that even after failure, they are still holding the specimens, the pieces together. Now moving to the flexural performance, the effect of the fiber type on the flexural performance. We have here the average residual strength, and this is the equivalent flexural strength ratio, which is a property that we obtain from one of the flexural tests. And we see, so these represent different dosages for each type. So this is type 1, 2, 3, 4, which are shown here. And we see for the most part, for synthetic fibers at least, we see they are all around the same values, same with the equivalent flexural strength ratio. But we have a jump in fiber type 5, which is Dramix 5D, which is a steel fiber. And this is something that we also anticipated because of the fact that, as I showed previously, the steel fibers have much higher tensile strength, around 333 ksi compared to 90 ksi, which the synthetic fibers have. That's why we have this jump in the flexural performance in steel fibers. This figure here shows the experimental modulus of rupture versus theoretical modulus of rupture, and this is just another way to confirm our experiments and give us confidence about our experimental procedures. And you see all of them are around the line of equality here. Now moving to the effect of fiber type on the impact performance, really whether it is the statistical tests or the figures here, we couldn't really draw any conclusions from this. So we see sometimes it jumps up. So even here, if you see at fiber type 3, most of the time we got values around 1 to 1.5, and then there's one fiber dosage that jumped over here. So the behavior is quite erratic for this test. One of the reasons is the fact that we had only one specimen. We didn't have any replicates. As I said, this test was not really a part of our proposal or matrix to begin with. We just did it just to see, to get an idea. But the fact that we didn't have any replicates and the fact that this test is very qualitative in nature. So you keep dropping the hammer till you see a crack visible by your eye, and then you drop the hammer again and again till it fails basically. And the criteria for failure is very subjective and qualitative in nature. And so it really doesn't give us much about the effect of fiber type on the impact resistance. And so a different kind of test, more sophisticated tests would be more beneficial in this case. Something like a compressive or a tensile strength where test where we have a variable strain rates applied and more quantitative in nature. That would be a better test for impact. But for our case, we couldn't really draw any conclusions here. The fiber dosage, if we look now the effect of fiber dosage and the different properties, as we expect, the slump really had very significant changes when we changed the fiber dosage. So around 0.2%, 0.39 or so, and then 0.54, and then 0.69% dosage. We see that the slump really drops a lot around. So here we have a loss of around maybe 70% or 60% in slump. So these values are the ratio to the control. So if you have little bit of fibers, slump does not change much, but as we increase the fibers, we see a very notable drop in the slump. And then if we average them, so the fiber type does not really affect the slump. It's only the fiber dosage that affect the slump. So we can't really average all of these. So these basically represent each fiber type. If we average them, we end up with a very good correlation, secondary correlation. But obviously this correlation would work only for our specific mix, which is, as I said, is a standard mix used by South Dakota DOT. So it wouldn't be applicable if once we change other properties. I mean, we change the cement content or the aggregate content and so on. So obviously we would need another correlation for that. Now moving to the effect of the fiber dosage on the flexural performance. Here I'm just showing the averaged values across all fiber types. And we see an increase as we increase the fiber dosage in almost all properties. So whether it's the toughness, the equivalent flexural strength ratio, the average residual strength, or the normalized effective modulus of rupture, we see an increase as we increase the fiber dosage, which is, and the correlation is really very good linear correlation in all of the properties, which, as I said, could be used to predict, this correlation could be used to predict the property, obviously assuming we are using the exact same mix that we used in our studies. But yeah, it's something that we would expect. The more fibers you have, the more bridging of cracks, and the higher the capacity would be of the concrete when it comes to tension, which means higher flexural capacity. One of our also objectives here was to try as much as possible to compare our values with the manufacturer's claims, and they actually matched pretty well. So we didn't have manufacturer claims for all the fibers, but for these two specific synthetic fibers, we had some manufacturer claims in the fiber data sheet. And that was for the, if we go back here, it was for the equivalent flexural strength ratio. So our study showed for a dosage of 358 for this fiber, this was the flexural strength ratio, 22, 30, and 46%. And for the other fiber, when it's 5, the dosage rate, then we have a 32% flexural strength ratio. Now, from the fiber data sheet, the values were very very close actually. So we have 22, 20, 30, 28.5, 46, 40.5. The dosage is slightly different here. So that's why we have a slightly less value. And then for this one, 32 and 35. So it's very comparable. So we conclude that really the manufacturer claims, at least for these two fibers, were really spot on when it came to this particular property. Now looking at the effect of the fiber dosage on the impact performance, again, when it comes to the first crack criteria, we don't really see any correlation here. For the failure, we might see an increase all of a sudden at 0.69%. But as I said, the results were really very erratic, and we didn't have replicates, so it's very difficult to make firm conclusions about the impact resistance for different fiber dosages. So basically that's main points or main basically findings from our results from our experimental setup and experimental procedures and results that we conducted here in our labs. So here this is I'm gonna now show you some of the conclusions, kind of summarize, and most of the conclusions that we obtained from our experiments, specifically our experiments. So the first conclusion, which is something that I didn't really show in this presentation, but there is something that we notice in the replicates, the specimen replicates. The difference in results between the specimen replicates for each test can be very significant for FRC due to possible difference in fiber distribution and orientation among specimens. So for each specific mix, for example, say the average residual strength property, we have 5 different replicates, 5 different samples. We can see, we usually average them, and that would be the value that we actually report. The values that are reported here in this presentation or in the report, those would be the averaged over all replicates. But if we look at the raw data, the replicates themselves, you can see that there is sometimes some significant changes. We believe the reason for that, I mean, when we compare it to conventional concrete, I'm saying, so in conventional concrete, we see some fluctuations in the replicates, but it's not as severe or as apparent as in our case in FRC. And this is something that we actually noticed in other studies in the literature, and this is something also mentioned by ACI, which we believe is due to the fact that distribution of fibers and the orientation, specifically the orientation of fibers, are very random. So once we mix and we cast the concrete, we really have no control over the orientation of each of the fibers. So they are randomly oriented within the concrete. And this basically resulted in us conducting another study, which we did during the summer, and we are actually now finalizing the final report, which is also a study sponsored by MPC, and we're going to be submitting the report soon. So this one really tries to predict these differences among the replicates based on the assumption that the reason behind it is the fact that the orientation of the fiber is very random in nature. Fibers have resulted in the reduction of compressive strength and mortise elasticity of concrete. Again, this is in our specific study. We can't really conclude what's the reason behind it. I believe we need further studies specifically targeted at compressive strength in order to come up with a reason behind this reduction in compressive strength. And as I said, this contradicts some of the literature studies. The type of synthetic fibers used in the concrete has no significant effect on any of the fresh and hardened concrete properties that were measured in this study. So as we saw in all of the properties, regardless of the fiber type, the concrete, the FRC really behaved similar to one another. That's for synthetic fibers only, but once we looked at the steel fibers, we can see some notable increase in the flexural performance in steel fibers. And again, this is most likely due to the fact that steel fibers have very high tensile strength, and all the synthetic fibers, they had comparably very close tensile strength to one another. Steel FRC has superior flexural properties compared to synthetic FRC, but it has the concern of being susceptible to corrosion. So this is something that we should always keep in mind whenever we're using steel over synthetic. But here we are just mentioning an example like jersey barriers, for example, since they are not directly exposed to the ice or salt, there might be a good application for steel fibers. Uh, Steel fibers are twice as expensive as synthetic fibers, but they can perform better or at least as good as synthetic fibers at half the dosage rate. So even though they are twice expensive, we can use half the dosage that we use for synthetic fibers and we still get the same performance. In our specific study, the most cost-effective synthetic fibers were these two, fiber mesh and photoferro. These are the ones that showed the best in terms of cost. All synthetic fibers were exactly the same in terms of performance. The ones that had the most cost-effectiveness is the fiber mesh and the photoferro. Slump decreases non-linearly with increase in fiber dosage, as we showed, which is something that we should keep in mind whenever we design FRC. For synthetic FRC with fiber dosages between 0.21% and 0.69%, basically the ones that we tested, data showed that an increase of 0.1% in fiber dosage results in an average increase of 74 pound-inch in toughness, 8% in equivalent flexural strength ratio, 37 psi in moles of rupture, and 81 psi in average residual strength. Again, these values are for our specific mix. They might not be the same if we have mixes that have different proportions, basically. Experimental results were in good agreement with available manufacturers' claims. The adopted impact test gave inconclusive results due to its qualitative nature and due to the lack of specimen replicas, as I said. So-cut surfaces of FRC cylinders showed uniform fiber distribution and no fiber balling, which indicates that the 5 minutes of additional mixings that we had on our laboratory mixes were adequate. Now, moving into our recommendations, we have different recommendations for design and for choosing the fiber type and construction and so on when it comes to FRC. And these recommendations are obtained or basically devised based on not only our experimental procedures, but also on the literature review studies and the interviews that we made with the DOT personnel. Higher slump values compared to PCC mixes should be targeted for FRC mixes in order to compensate for the reduced workability. So this is something we, as I said, we should keep in mind. If we have a conventional mix that has a slump of 5 or 6, for example, and then we introduce fiber into the mix, we should keep in mind that this would reduce the slump and maybe consider adding a super plasticizer or so. Fine to coarse aggregate ratio should be increased in order to provide higher mortar content that is helpful to increase workability, minimizing fiber balling and reducing crack widths. And these are based on some of the literature studies, basically. Up to 20% and 15% reduction in compressive strength and modulus of elasticity respectively should be taken into consideration when designing FRC. That's based on our study. As I said, other studies showed contradictory conclusions. That's based on our studies. And we think we should keep it in mind till further studies are made on this specific property so that we know the reason behind it and whether we can eliminate this reduction. Now, the recommendations for the construction, manual consolidation should be completely avoided. As I said, it's very difficult to work with FRC and to make sure it flows into the forms, and to make sure the fibers are uniformly distributed. It's better to have a vibration, some kind of vibration when it comes to casting concrete FRC. FRC tinning should be modified by either reducing the tinning angle, turning the tinning rake over, or grinding the tinning grooves after hardening. So these are recommendations based on some of the interviews that we did with some DOTs that had previous experience with FRC, and they had this issue where they pull, when they do tinning, they pull some of the fibers off the surface of the concrete, And so these methods could be used to avoid pulling these fibers from the surface of the concrete. A burlap drag or a broom should be used instead of a carpet drag in order to avoid pulling of fibers from the surface. So this is the same, something that was advised by other DOTs that had experience with this specific issue where they had the fibers being pulled once they do a carpet drag on the pavement. Now, some recommendations for fiber type and dosage. To minimize fiber bowling, fibers with low aspect ratios should be used. So we should always use try to make use of fibers that have low aspect ratio, and in our case the Fortaferro is the one that had the lowest aspect ratio, and it was also the most cost effective. So this specific fiber in our case for the fibers that we tested would be the ideal one considering all its like basically effect on the properties and its cost effectiveness and the fact that it has low aspect ratio, which makes sure that we minimize the fiber bowling. Steel fibers should be avoided in components that would be exposed to chloride penetration. So this is basically why steel fibers is usually not used in applications where we have very harsh winters. And a more detailed, so these are kind of the summary of the recommendation. A more detailed guideline that we provided for South Dakota DOT could be found in the report that was submitted to both MPC and South Dakota DOT, which should be, as I said, attached in this webinar. Now, for future research, we have some ideas which could be studied. So the first one, instead of the empirical correlations that are usually obtained from experimental results which cannot be guaranteed to work under all circumstances due to limitations in the testing matrix, it's better to come up with theoretical correlations and then verify them against comprehensive experimental results obtained from very different mixes. So the fact that we can only do that much mixes, I mean, we cannot, so we don't have the privilege to do as many mixes as we want, as it will cost more the more we use mixes, and so we always have the disadvantage of replicates. We can replicate specimens, but if we want to replicate mixes, then that would make an additional cost to us. And so a more ideal, and the fact that the fiber distribution as well is very, the fiber orientation is very random in nature, that makes trying to come up with a theoretical correlation between the fiber dosage or type and these properties of concrete something that would be interesting, which basically would permit us to make virtually limitless theoretical correlations, limitless theoretical experiments, maybe I should say, which is, so once we come up with theoretical correlation, we can basically do any combination using any software, like by writing a program that does that, which saves us having to do more experiments in the lab. So this way we can only do few experiments using completely different mixes and then compare them to our theoretical results. And this, as I said, this is one thing that we tried to do in a recent study which we conducted in the summer, as I said, trying to kind of predict the erratic behavior in the results that we get in the lab among the different replicates of specimens. So this is something that we did in summer, and then we are finalizing the report, which will be submitted soon to MPC. The effect of other aspects of the mix design, such as mortar content, water to cement ratio, coarse aggregate, and cementitious materials should be studied. So all of these were fixed in our case. We didn't change any of these. So this is something that could be studied further in the future. Other more informative workability measurements such as rheology should be explored in order to better correlate fiber doses to workability. As we know, slump, even though it's a very widely used parameter, and it's very convenient and very easy to perform, especially in the field. That's why it's typically used. But in reality, it's not an accurate representation of the workability of the concrete. And so it would be interesting to try and look at the rheology, which is a two-parameter test, which would be more representative of the consistency of the concrete or the workability of the concrete. Effect of fiber type and dosage on impact performance of FRC structures should be studied using more reliable instrumental impact tests, incorporating compressive and tension loading with variable strain rates. As I said, the impact test that we conducted is very qualitative in nature, so it's not very reliable, and so we recommend in the future using more instrumental kind of tests where we can apply variable strain rates and then obtain some compressive and tension properties, which would be more quantitative in nature and would give us more robust conclusions. And with this, I conclude my presentation. Thank you all for attending today, and please feel free to ask any questions.
Okay, and I want to thank Dr. Godbon. In advance now, I know we'll probably have some questions. I know I have some questions I want to pose. And again, I would recommend that any of you out there that are listening to post those some questions you might have in the Q&A area. And I want to point out too that we sent out a PDF, and I noticed on my PDF that we sent out that some of the test results were blocked by a photo overlaying it, and that was due to how slides are made with the animation. We have updated that. We'll see. It'll definitely be loaded on our LMS, a version that shows those as separate slides. So anything that was blocked in your paper version will be shown then in the later version. So, but anyway, in today's presentation on slide 16, that Dr. Gadvan showed those clearly without the photo overlaying them. So thank you for that change on that. Some of the questions I have. In the slump test, is there a concern about the mix flowing around reinforcing in a structural member? And did you do any type of sampling where you did cast that around reinforcing and determine if there's any voiding? I think you'd have mentioned it in the research, but was there anything done like that, Dr. Gavin?
So of course, yeah, since we have a lower slump, you would expect a concern when it comes to the concrete flowing around reinforcements. But as I said, that's why usually internal vibration or external vibration is suggested by ACI as well. So they always say you have to always use vibration when it comes to FRC to make sure it flows as you want around reinforcements and within the form. Now in our case, in our labs, we didn't really perform any test like this, like trying to cast concrete within steel, around steel reinforcements. But this is something that was pointed out by some personnel from DOTs around the US. They told us during the interviews that they really have to do vibration all the time whenever they use FRC to get rid of this problem, which is the low slump, basically.
Okay, and speaking of the additional vibration, there's no ACI guidance about maybe about the amount of additional vibration is there, or is there any advice on that?
It's usually typically the same as what you would use for conventional concrete.
Okay.
So say you have a conventional concrete with very low slump, then you would use vibration. So it's kind of the exact same thing that we use with FRC. So nothing really different between it and the conventional concrete.
Okay. And getting back to that flowability issue, I know that on December 12th we have a webinar for those who are listening on self-consolidating concrete in pre-stressed beams. And make, which made me think, is there a possibility of research on a combination of fibers and self-consolidating concrete, or and has that been found in the literature search? As in, and again, to take away some of that concern about flowability
Yeah,
around.
I think that would be interesting. Actually, as I mentioned during my presentation, we did some like very. It's a very short study though. We can't really. It was not meant for self-consolidating concrete. We did it in the summer, some experiments in the lab, and we actually used several mixes, a total of 8 mixes, and some of the mixes we tried to design them such that they are as close as possible to an SCC, which basically make them very flowable. In that case, I mean, by eye inspection, it seemed that the concrete was, even after adding fibers to it, it was pretty much flowable, and I didn't seem to see any need for vibration in that case. But as I said, that's just like a mix or two that we did, and the purpose of the study was not to see the self-consolidating concrete with FRC, but it was something that we noticed in our experiments.
Okay, thank you for that. So I I also wanted to ask about that compressive strength. Your control compressive strength, I think in the report shows it was quite high at 7,700. Is that about right? Um, and was that shot, did you put that high because of anticipated reduction, or because I think that's higher than most structural design concrete, unless you're working for high performance concrete.
Uh, I we didn't really aim for a certain compressive strength, to be honest. So we just used the mixed design that was suggested by South Dakota DOT, because they had a mixed design which they actually use most often in their mixes, and they were interested in seeing how would that specific design behave when we add the fibers to it. So we used their mix exactly as is, and then that was the value that we obtained from that specific mix. So that, I mean, the fact that it's a little bit high tells me that I don't know if there is something that was done during the lab experiments which which caused it to go higher than what we would expect, and that's why the fiber ones showed a reduction. That might be the reason, but we can't really be sure about it. So as far as we followed the procedures in the labs, we believe we should have obtained the results as accurate as possible. But yeah, it's very difficult to know the reason behind this reduction unless we do further studies,
Mhm.
as I said.
Yeah. And I guess the point is it looked like the resulting compressive strengths were quite high. We even if there was a reduction, they
Yeah.
still were pretty good for a design component.
Mhm.
Um, and okay. I do have a question from one of the attendees. This is Dr. Gadban. You mentioned the reduction in compressive strength. How does this compare with other literature results? What is the mode of failure for this reduction? And is there slip occurring at the fiber mix boundary? Thank you. A couple
So
questions there. So you can re-ask me you can ask me to restate that if you wish, but
can you say it again, just to, yeah.
okay. You mentioned reduction in compressive strength. How does that compare to the literature results?
So as I said, so for this part of the question, so the literature results had very contradictory conclusions that I said. So there were some studies that mentioned an increase in compressive strength, some results mentioned a decrease, and some results mentioned a no effect, basically. So our results were aligned with one of these, but 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 some other research studies were completely contradictory, and even in those studies, they didn't really come up with any explanation for that reason behind the increase or the decrease, or I mean, the no effect conclusion would be the most intuitive one because we don't expect fibers to do anything to compressive strength. But those research studies that had an increase or a decrease didn't really provide any explanation for the reason behind it. So really, when it comes to the literature review, we align with some studies, but we contradict other studies.
Okay. And then second part of that question is, what is the mode of failure for this reduction? And I think the two questions go together. Is there slip occurring in the fiber mix boundary? You know, and if you understand that.
Yeah, I mean, uh, to be honest, this is something we don't have it documented in our report. We didn't take a look at. But from the one that I showed here, so I showed a picture, and this was for all mixes. So this failed specimen is exactly the same failure mode for all of them. So the specimen is still intact, and that tells us that the fibers are still working. They are basically holding the pieces together, as compared to the conventional concrete where the specimen would completely crumble. So the fibers are actually holding the specimen together, but whether there was any slipping between the interface between the fibers and the cement paste or the concrete, uh, we're not really sure. But really, if whether there was or not, uh, I'm not really sure whether this would result in a reduction in the compressive strength. I don't know.
Okay. Um, and again, Luke Brevard asked that question. If you have any other follow-up on that, and just put it in, be sure to ask that additional question. Um, and then I just wanted to point out that my memory of concrete flexural design is a little dated, but it seems like your modulus of elasticities resulting were quite high as well. I'm thinking that our design modulus elasticity is about 3,000, and you're still running, resulting in about 4,500 to 4,800 check. Am I correct about what design modulus elasticities are for reinforced concrete?
Well, it depends on the compressive strength of concrete. So whether, I mean, as the higher the compressive strength, obviously
Right.
the higher the modulus of elasticity, and it correlates really well actually with the compressive strength. So the fact that we have a slightly more compressive strength than normal concrete, say not high strength concrete, uh, basically results in also a higher modulus of elasticity. So if we use the ACI equation, which was 57,000 times square root of f prime c, we get very good correlation, uh, as I showed in one of the slides here. So, which is here, yeah. So this is the experimental one, and it's matching really well with the theoretical one. And the theoretical one really depends on the compressive strength. So yeah, the measured modulus of elasticity is exactly what we expect given our compressive strength.
Okay. Thank you.
Mhm, mhm,
So, are there any other questions for Dr. Godman? This is a very interesting study. So,
mhm.
and we've got him here on the line. So, if you want to, if something is haunting you, please type it in. And if not, I think we're about ready to wrap up. It was a very good presentation, and this is a very good research project, and something that is definitely necessary. When we've found this study through the MPC process, Mountain Plains Consortium Research Area, we knew that this was one that is on the cutting edge of and something that's necessary to know for implementation. This is something that fiber reinforced concrete is something that's definitely of interest to everyone because the whole world, all transportation organizations um, behind are behind on funding. So everyone's looking for how to stretch the concrete dollar the asphalt dollar and
Yeah.
the steel dollar. So
Mhm.
these things are definitely necessary, and we thought this research was probably something that people need to have in order for them to make a decision if they're going to try to use this product. I'm aware that some of the states that we have in our group have dabbled in this. There is another question on what type of aggregates and sources were used. Was there anything unique about that, or were they typical South Dakota DOT, South Dakota aggregates?
I think they were quartzite. That's those. Basically, yeah, they were typical, not really any. The one that were suggested by South Dakota DOTs, basically. So I think
Okay.
it was provided by them. I'm not sure, but yeah, I think it was provided by them.
Okay. Um, Good question, by the way. Thank you about that. And just in case you were wondering then if there was anything maybe of a higher than normal standard. So it looks like you were working with them so that they were evaluating what most of the items that they would use in a typical construction project.
Hmm.
Okay.
Hmm.
All right. Let's see. Okay. Another question here. Our viewers is curious if it would be possible to use recycled materials for FRC to both improve surfaces and reduce landfill volumes. Again, everybody in the world, there's a lot of push to put recycled materials into our highways. So,
Yeah,
is it
I
possible?
guess.
Go
Yeah,
ahead.
I guess that's a good research topic, I should say. It's a good idea. I mean, why not? I mean, we see a lot of studies where they try to use recycled materials within in concrete. So why not try it with the FRC? It's not a stretch to try and do it for FRC as well.
Okay. And again, there was one again about the follow-up research. Will there be follow-up research on the inconsistencies in compressive strength uh, values?
Well, so far we have nothing really in that nothing that we don't have anything currently working on the specific compressive strength problem. But as I said, we had another one which is almost finalized now, a very short project, which uh, which is really looking at the the fact that the results among different replicates within the same mix are very erratic in nature. So this is one we are looking at right now, but nothing as of now for the compressive strength.
Okay. Um, Pause here for a little for any additional questions. We'll pause for about 5-10 seconds. Um, and I still want to reiterate and emphasize how important this type of research is. Uh, I I don't know if it's common across all four states, but in our city that I live in, fiber reinforced flat concrete, slab concrete is commonly used in uh, residential operations. And I'm not aware that DOTs have really embraced it as much. So it's common in the private sector, but it's probably not as common in the public sector, mainly because of some of these uncertainties that this research helps to clear up. And so I just wanted to leave everyone with that thought as well. And any comments on that, Dr. Gadban?
Yeah, I think it's very nice, and that's one of basically the main reasons why we conducted this research. It was a suggestion by SD. They didn't have many FRC implemented in their projects. They had a couple of projects that were done way back, maybe 20 years ago. So maybe another project that was a little bit more recent, but not really much done because they didn't have enough information. Like there is too many uncertainties about FRC, and that was the spark for why they wanted such a project to be such a research to be conducted in the first place. And I think this is something we should strive to do, try and remove all of these uncertainties around the FRC and make sure it basically dives into the applications when it comes to transportations agencies, where they can use it and be confident that it can give them a higher life expectancy.
Okay. Oh, I'm not seeing any more questions, but I want to thank our presenter, Dr. Godben. That was a very good research project. And again, I want to encourage our viewers to consider that maybe these things these topics be applied to the real world. That's the intent of the research, so that knowledge can be gained and then it can be used in application. So I believe this research project brought everyone a lot closer to a confident application for that. There are benefits to fibers, and it looks like that some of those benefits have to be accommodated in the design, but they can be accommodated from the looks of it. So.
Yeah. Yep.
All right. I'm not seeing more questions. Thank you. Everyone, please feel free to refer this recording to anyone else in your organization that you think should see it. Again, it'll be on our learning management system within a couple of days. We say a week, but it will. And I think we're just getting a thank you from our viewers, Dr. Godben, and
Thank you very much.
we thank you too. And have a good rest of your day, and to you and to the viewers. Thank you.
Thank you. You too.
Thank you, gentlemen.